Greetings, members one and all of the Salivation Nation. 2D Gold. Let's explore! That's right, A Touch of Gold and Silver is the name of this article from phys.org, a very interesting website that talks about things like nanotechnology, technology, physics, and the like. And sometimes metals make their way into the mix. And this particular article here talks about gold and silver, especially gold here, and its conductivity in very thin layers. So metals are usually characterized by a good electrical conductivity, and it applies in particular to gold and silver. However, researchers from the Max Planck Institute for Solid State Research in Stuttgart, together with partners in Pisa and Lund, have now discovered that some precious metals lose their property if they are thin enough. The extreme of a layer only one atom thick thus behaves like a semiconductor. This once again demonstrates that electrons behave differently in the two-dimensional layer of a material than in the three-dimensional structures. The new properties could potentially lead to applications, for example, microelectronics and sensor technology. One might think that gold leaf, which is only 0.1 micrometer thick, is actually quite thin. Far from it. It can actually be several hundred times thinner. For example, the research team at Ulrich Stark and his former doctoral student Steven Forti have successfully created a gold layer only one single atom thick, two-dimensional gold, so to speak. And that should sound familiar. We're going to get to that here momentarily. Stark is the head of the Interface Analysis Facility at the Max Planck Institute for Solid State Research in Stuttgart. His team has long been working on the border between three-dimensional, voluminous, and two-dimensional planar materials. Solid-state researchers are interested in this transition because it is associated with changes in certain material properties. This has previously been demonstrated in two-dimensional carbon or graphene. You've heard me talk about it on this channel. We've actually talked about how graphene could actually be a threat to silver and gold, especially silver as an electrical conductor. Among other things, its electrons are significantly more mobile and allow the electrical conductivity to increase to 30 times that of the related three-dimensional graphite. Wow, pretty amazing. So gold atoms are pushed between graphene and silicon carbide in this next section here. For many metals, producing layers of material just one atom thick is not an easy task. With classical deposition methods, gold atoms, for example, would immediately agglomerate into three-dimensional clusters, explained Stark. His team is therefore working on with a different method, intercalation, on which they did pioneering work around 10 years ago. Intercalation literally means sliding something in between. That's what she said. And that is precisely how it works. The researchers start with a silicon carbide wafer, using a process they developed themselves. They first convert its surface into a single atomic layer of graphene. If we vaporize sublimated gold into the silicon carbide graphene arrangement in a high vacuum, the gold atoms migrate between the carbide and the graphene, explains Forti. The former Max Planck doctoral candidate is now doing research at the Center for Nanotechnology Innovation in Pisa. It is not yet fully understood how the thick gold atoms get into the interstitial space, but this much is clear: how higher temperatures favor the process. And so it's fascinating how this works. It's incredibly complex. The team had also applied the intercalation technique to other elements, including germanium, copper, and gadolinium. Yet, according to Forti, the main focus was the influence and the properties of graphene. In the case of gold, however, it was found for the first time that the intercalated atoms arrange themselves in a regular, periodically reoccurring two-dimensional structure, crystalline, along the silicon carbide surface. If the intercalation is carried out at 600 degrees Celsius, the graphene layer prevents the gold atoms from agglomerating to form drops, says Forti about the function of the carbide layer and the sandwich structure. In other words, they don't clump together in 3D clumps there. And so they're saying a gold layer consisting of only two atomic layers conducts like a metal. Now, that's fascinating that they are able to do that, to make that work in this particular way. So the successful preparation of the gold layer of one atom thickness was only the first step. Subsequently, the extremely thin materials and their possibly special characteristics became interesting for the researchers. They can indeed show that the extremely thin layer of gold develops its own electronic and semiconductor properties. To compare, the electrical conductivity of a voluminous three-dimensional gold is nearly as good as that of copper. And by the way, silver is the absolute best, because theoretical considerations forecast a metallic character for pure 2D gold. The semiconductor finding was somewhat surprising. Interactions between the gold atoms and either the silicon carbide or the graphene carbide obviously still play a role here. This influences the energy levels of the electrons, says Stark. Semiconductors are essential materials in microelectronics and other fields. For example, electronic switching elements such as diodes or transistors are based on it. Stark's team can envisage some typical semiconductor applications for the new 2D material. The second layer of gold atoms again gives a metallic character and thus influences the electrical conductivity. By varying the amount of sublimated gold, we can tightly control whether one or two layers of gold form, explains Forti. It would therefore be conceivable to use components with alternating single or double atomic gold layers. This new manufacturing method would then have to be suitably combined with common lithographic methods of chip production. For example, diodes significantly smaller than conventional ones could be produced. Just amazing how this nanotechnology works. According to Stark, the different electronic states of single and double layer gold could also be used in optical sensors. And here's the electronic effects also in the graphene layer. Another application idea results from effects caused by the intercalated gold in the adjacent graphene layer, which apparently depend on the thickness of the gold. A gold layer 1 atom thick causes an in-doping of the graphene. This means we obtain electrons as charge carriers, says Forti. At spots where the gold is 2 atoms layers thick, exactly the opposite, p-doping happens. There, missing electronics positively charged, so-called holes, act as charge carriers. The gold also enhances the interaction of the plasmons, which are fluctuations in the density of charge carriers, with electromagnetic radiation. A structured, alternating arrangement of N and P doping in the graphene could thus be used. For example, it's a highly sensitive or yet high-resolution detector array for terahertz radiation like those used in materials testing, for security checks at airports, or for wireless data transmission, says Stark. It seems like it would be very fragile, too, technology. Any little thing gets in there, it has to be completely sterile and the like. That's one of the drawbacks with graphene production. There's got to be absolutely pristine environment. Anything 1-2 atoms thick, you can only imagine what could upset that array. Stark's team has already taken the next step in the production of two-dimensional precious metals layers. Also, in an intercalation experiment with silver, a strictly crystalline two-dimensional silver layer formed between silicon carbide and graphene. And what's more, even this metal, which is usually an even better electrical conductor than gold and copper, becomes a semiconductor when reduced to two dimensions. Wow! The initial results indicate that energy required to make the silver layer electrically conductive is probably higher than for 2D gold. So there you go, folks. This is one area on the electronic world where gold beats silver. The only other place is the fact that it's not reactive, so it's very important for use for in space and other applications where reactivity is a factor for sure. The semiconductor properties of a component made from this material might therefore be thermally more stable than those of gold, says Stark about possible practical consequences. Okay, well, that's interesting. Yes, indeed. Well, fascinating indeed. So there you have it. 2D gold, maybe even 2D silver. Post your thoughts. It's amazing the technology involved and how they're utilizing the precious metal for this kind of application. Let me know your thoughts below about this exciting story. I would like to extend a multitude of gratitude to you all for taking the time to watch and encourage you to please rate and please share and then finally comment, and after that subscribe if you haven't already. Take care. See ya.